Good morning. I think it's probably very ringy in here today, but oh well, c'est la vie. Okay, so this is Kali and I'm going to be talking about some physics stuff. Let's talk about gravity. Just a way of thinking about, a really easy way of thinking about why gravity is what it is and how it works. I just think of it as falling downhill all the time. So, I'm going to draw circles, but let's make these circles represent an energy density. Okay, the size of the circle, this area, all of space, all has the same energy density, right? If they were larger, that would mean it was less energy dense because it would be taking up more room, unit energy, let's say. Okay, so, but wait, let's make the energy density really high here. Basically, there's the simplest way of thinking about gravity is just that if it's more dense, then unit graph is smaller, like the mesh density is smaller. And if you made any one, like this, if this was a gravitational field, it would sort of be in 3 dimensions, right? And all of these would be getting away. This is close to the surface where there's a very high energy density just because of gravity itself. But it's like, because there's a lot of stuff, it has a lot of energy, which warps space, which makes a downhill slope. Regardless of where it is, since the energy density gets concentrated, the mesh density effectively means you're falling downhill. You want to always go where the most dense is because it takes up the least room. So that's sort of like a simple way I find of just thinking about gravity so that it's like not complicated and really does communicate all the essentials. Because light would be transverse and that would be bent a little bit by this and a little bit by this. And then the other thing is the Hubble, sorry for the jiggles, this is between my legs. Anyways, between my knees, there we go, Hubble tension, or the Hubble Doppler. Okay. We'll do this again. Here's some space-time. Here's some space. And there we go. Nicely even space, uncurved space, right? Flat space. Now, let's say your observer here. Boo-doo, boo-doo, little nose, mouth. Okay, your observer, and you're looking out from you. As you go further away from you, there's more planets and galaxies in space, and the mass increases away from you, cubically, because these things expand. So every light year you go out, there's also, the light year gets wider, and it also gets larger volumetrically. So the mass away from you is constantly increasing. If the universe is infinite, this would be a parabola, which, though the slope is constantly increasing, but it continues forever, and it just gets lower and lower. So there's our piece. But we've added some gravity to it. So now we're going to take these lines and I'm going to put them exactly the same. But if you notice, because this is splayed, this is now further than it was here. Because it's splayed out. which would lower the frequency because now the wavelength unit space is here, now unit space is there. Hubble Doppler. And then you're like, well, yeah, but why would there be blue shift around local gravity things? Well, you're in the middle of the totality. So it gets red because mass increases away from you. But let's even make a little, we'll make a little local, there's a black hole story thing, right? Well, these would go like this, right? Following the curve of the local space. And notice how even to us, they get closer and closer and closer and closer. Because this is a convergence. All convergences are constrictions and go up in frequency. Space is tightened. The totality of space, though, around us is nothing but roomy, and therefore everything gets pulled a little bit apart. This is the Doppler shift. This is the Hubble Dopplers, just space, the immensity of space, warping space-time around us, pulling everything because there's infinity around us. And this is why that was why the blue shift still happens for local things. Okay, so this is my little thing. Anyways, good morning.